Hello, my name's Martin Woolley. I work for BlackBerry's developer relations team and I'm based in the UK. Now today, together with my colleague John Murray, who's also from the same team, we're going to be talking to you about Bluetooth Low Energy on the BlackBerry 10 platform. And in particular, of course, we're going to look at what developers can do with Bluetooth LE. So here's our agenda. We're in the introduction right now. And shortly I'll hand over to John and he'll give you a theoretical overview of Bluetooth Low Energy technology. When he's done, he'll hand back to me and I'm going to show you an application that John and I wrote for BlackBerry 10. It's called Heart Monitor and it's a heart rate monitor which athletes might use. And we'll look at the app, we'll look at the basic approach to exploiting Bluetooth LE from code, and we'll look at the code itself. And then we'll close. Okay, so let me hand over to John for the theory part of the session.
Thanks for that introduction, Martin. Now we're going to take a closer look at the Bluetooth Low Energy architecture itself. So you thought you understand Bluetooth? After many years of trying to go faster, Bluetooth underwent a bit of a revolution a couple of years ago. It started to get smarter. Starting with a blank sheet of paper, Bluetooth was modified to become optimized for ultra-low power devices. So in what sense is it new and how different is it? The discovery and connection process is much more efficient. The application model is different. It's much more lightweight. And the packet sizes have been modified to be much smaller. All these go together to basically use less power. Of course, it still exploits classic Bluetooth in that it reuses many of the classic BT components, like the radio architecture, many of the APIs that already exist in classic Bluetooth, and the existing link layer packet structure. By focusing on power consumption, Bluetooth became Bluetooth Low Energy and became smarter rather than faster. You can't stream things like audio over it, but you can actually do many more interesting things with it. Bluetooth Low Energy devices are designed to be run on small button cells like this one. You'll find Bluetooth Low Energy in smart devices. For example, a smart toothbrush that takes your temperature as you brush your teeth and logs your information on a website. In fact, it's an enabler for the Internet of Things, where small devices can all be connected to the Internet and be interacted with. Like any good architecture, Bluetooth Low Energy is layered from the physical to the application layers. As developers, the bulk of the Bluetooth Low Energy stack is probably of little concern to us and will generally be concerned only with the top layers. However, it is instructive to have some appreciation of the radio layers, though, and why Bluetooth Low Energy is so resilient. Bluetooth was designed to work in radio environments that were inherently hostile. Interference from many other devices that share the same spectrum was around, for example, Wi-Fi, cordless phones, even microwave ovens. Bluetooth Low Energy retains this capability but has a slightly different channel structure that helps low power consumption by widening the bandwidth of each of the channels that it hops around. You can see from this diagram that it's sharing bandwidth with Wi-Fi connections, Wi-Fi access point, yet it's still able to provide a robust service by hopping around. Bluetooth Low Energy devices use a number of different roles to interact. These are optimized to reduce power consumption by reducing the complexity of the classic Bluetooth discovery and connection procedures. So a Bluetooth device which has an advertiser role is basically saying, here I am, here's the capabilities I have, who would like to connect to me? A scanner, for example, is trying to discover what Bluetooth Low Energy devices are present in its environment. Who's there? Who is there that I can talk to? Once the device that's been performing scanning discovers a suitable device that's been advertising its services, it can then choose to initiate a connection to that device. Once two devices have connected, they adopt the roles of master and slave, where the master basically sends requests to the slave device and the slave device responds to requests from the master. So it's an asymmetric type of environment. This is actually reflected and visible in the application level, in the roles of client and server that are used in this context. As developers, we will work with services. A server hosts services which contain characteristics. These are sort of like values that can be read and written. I'll say more about this later. Servers are usually small devices like heart rate monitors, thermometers, etc. Clients interrogate these services and read or write their values. Clients are typically devices like mobile phones, such as a BlackBerry 10 device. Servers, as well as responding to requests for data from clients, can also emit events called notifications and indications. The difference is that indications require an acknowledgement from the client, while these notifications don't. What makes characteristics interesting is that they're more than just numbers, strings, or other values. They're identified uniquely by UUID. That's in fact registered with the Bluetooth special interest groups. UUIDs can have two types, short ones 16 bits or long ones 128 bits. You can go and look up the definitions of well-defined services and their UUIDs and characteristics, and this as a developer should be one of the first tasks that you do when developing an application which communicates with a Bluetooth low energy device. Characteristics are also used by architecture to identify the device itself and its various attributes and capabilities. Characteristics have permissions. You can require that they only be read or perhaps allow them to be written. They also have other permissions that can protect against malicious manipulation. For example, it's possible to ensure that a characteristic might be protected by an authentication procedure or perhaps even an encryption procedure. Characteristics have scales associated with them to place the values in context. So temperatures may be measured in Celsius, Kelvin or Fahrenheit. Pressures may be measured in millimeters of mercury, newtons per square meter, pascals or bars. So let's have a look at how you can examine the characteristics of a device using some useful tools. What we have here is a very useful tool from Texas Instruments that can be used to help you as a developer to probe a Bluetooth device for characteristics and services. We scan the Bluetooth devices in the nearby vicinity by clicking the button there, and once the scan is complete we can see that we've identified a Bluetooth low energy device. If we connect to it, we can see in the log window here that there's some traffic related to that connection. In order to find out what services or capabilities the device has, let's probe it a little bit further using the GAT menu. We send a request and we can see here a number of the handles that have been identified with various attributes that are available on the device. We can ask for more information from the device and you can see that it's been completed, and you can identify services of various types, GAT services, and you can also see the heart rate measurement service down there near the bottom. Clicking on any of the attributes and characteristics again allows the device to report on these values so that we can see what they are. Once we've finished, we can terminate the connection with the device, and then we're ready to go and write our application.
Thank you, John. So now let's turn our attention to a real BlackBerry 10 application that John and I wrote and talk about how that works. Now, the application's called Heart Monitor, and it works in conjunction with a Bluetooth LE enabled heart rate monitor. And In approaching this project, we did some reading. We read about the Bluetooth heart rate profile, which is one of the standard profiles. You can go and read more about that in our knowledge base article. And we acquired a heart rate monitor device. This particular device is depicted on screen. It's a Wahoo Blue fitness heart rate monitor. And it straps around the chest of the athlete, or if no such athlete is available, someone like myself, and it measures the athlete's current heart rate, transmits it to a connected Bluetooth device using something called GAT notifications, and amongst the data it transmits is the heart rate measurement itself, which is expressed in beats per minute. So John and I developed a BlackBerry 10 application using the NDK, the Native Development Toolkits, and the Cascades framework for user interfaces. And we used this to receive heart rate monitor data in real time, to display the current beats per minute measurement, maintain some statistics, average, minimum, maximum, and to display a real-time chart, a line graph, as that data came into the device. So let's take a look at the device with its application working in real time in a short video fragment, and then we'll have a look at the code behind it. So here's our application, and it's just started receiving data from the heart rate monitor, which is strapped around my chest. You can see my heart's going a little faster than usual, actually, probably because I'm doing this narrative. And features of the UI include the current heart rate value displayed at the top, and it's pulsing in and out in time with the measured heart rate. And you can also see, coming in from the right hand side, we have a line graph that we're building in real time showing the variation. That was done using JavaScript, and that's a WebView component in Cascades. There we go. Winding on in time, you can see the way the values are varying, and we're maintaining some statistics, the minimum, average and maximum values measured so far. And there we have a full graph, very nice. So let's talk about how we went about developing the heart monitor application. From a coding point of view, there are three things we need to address. There's some initialization to do. We need to equip our application and our BlackBerry 10 smartphone with the ability to discover other Bluetooth devices in the vicinity, figure out which of them have the heart rate profile and service running on them, and do some filtering. And we also need to implement the monitoring functionality whereby we receive heart rate data over our Bluetooth connection and use it. So let's have a look at those one at a time, starting with the initialization stage. So here we are in the code for the heart monitor application. This is the Momentix IDE, part of the BlackBerry 10 NDK. And I've gone straight into one of the key classes in our application, the Bluetooth Handler class. Now in the constructor for Bluetooth Handler, which we're now looking at, you can see I do a number of things. Number one, I call the API function BT device init, and this initializes the Bluetooth library, essentially. I also make sure that Bluetooth is switched on, and I use a combination of BT LDEV get power, LDEV means local device, and BT LDEV set power to ensure that Bluetooth is currently enabled. And then the final API call that I make that I want to make you aware of is I call an initialization function to provide the GAT subsystem with some function callbacks to use as the status of GAT service connectivity changes. And you can see above my constructor there, I've declared a struct containing a number of function pointers there. So there's my GAT callbacks struct, which I pass as a parameter to my BT-GAT init function. So that's the initialization stage dealt with. So back to our high-level recipe, the next thing we need to take care of is device discovery and selection. And I haven't actually shown you yet how this manifests itself in the application. So let's start there with a video clip of the application discovering other Bluetooth devices, and then let's have a look at the code behind this area. So we select the scan function. This initiates scanning for other Bluetooth devices. When the search is complete, we get shown those that are available, and we can select the one we want to work with from the user interface. So now let's look at some of the key code behind the device discovery and selection part of our recipe. We implemented the device discovery functionality in our device listing class. Let's take a look at some of the key API calls that we make. We kick things off by calling BT disk start enquiry. So this initiates the device discovery process. Now this process runs in a background thread and it's quite asynchronous. So we delay to give it time to scan around and find any devices that are nearby. And then we cancel the inquiry process, the scanning process. Once we've done this, we call BT disk retrieve devices, and this returns us an array of BT remote device objects, those being descriptors for the devices that were discovered in the scanning part of the process. We then examine each device to determine whether or not it is running the heart rate service and therefore of interest to our application. So we iterate through our array of remote device objects, and for each one we ask the question, is it a heart rate monitor? Let's take a look at the way that logic works. So we have a function we wrote here called is a heart rate monitor, good name, does exactly what it says on the tin. And you can see that what we do here is, first of all, we ask some questions about whether the device type is a low energy device. So the API supports that with some handy constants. And then we retrieve an array of the GATT services that the device supports. And having done so, we iterate through that array of services and we look at the identifier for each service, and each service has a UUID that uniquely identifies it. And we say, is this the heart rate service? And we do so by comparing with a constant that we defined elsewhere. So there it is, HR service UUID is our constant. It has a value of hex 180D, and that's the defined value for the heart rate service per the Bluetooth specifications. So we scanned for nearby devices. We had a look at the services running on each of those devices to determine which ones supported the heart rate service, and we did some filtering, presented the user with a list to select from, and picked the device to work with. So let's now move on and look at the monitor stage. We've now got a device, we know it supports the heart rate service. Let's set things up so we can start to receive and use heart rate data from the heart rate monitor. So here we are back in our Bluetooth handler class, and we're looking at the method receive HR notifications. Key thing to focus on is this call. We call the API function BT GATT connect service, and we provide a number of parameters: the device address, the one that we selected during discovery, and the UUID of the heart rate service. Now cast your mind back to our initialization stage, because one of the things we did there was set up some callback functions for GATT connectivity events. So as soon as we successfully connect to the heart rate service on the device that we chose, this function, one of our callback functions, GATT service connected, gets called. So in GATT service connected, we call BT GATT reg notifications, and we provide a callback function, which I called notifications_CB. We'll look at that in a moment. We're basically saying we want to receive notifications from the device. We then have to indicate specifically what data we want to be notified about from that device. So the process then proceeds as follows. We find out what characteristics, data types, are supported by the device via this GATT service, allocate some memory, and then we obtain a list of the GATT characteristics that this service on this device supports. We then iterate through that list, and we basically have a list of structs, each of which has information about the characteristics supported by this service. And we examine each one, and each characteristic has a UUID as defined in the relevant specification. And you'll see here I've defined heart rate measurements with the hex value 2A37, which again, check the specs, you'll see that that is the ID for the heart rate measurement characteristic. As soon as we find the characteristic that has that UUID, we store two handle values. Now, handles are like temporary identifiers allocated by the Bluetooth device to a particular variable, if you like, that it has available within its service, and which is of a certain type defined by the characteristics UUID. And it's the handle that we're interested in, specifically the handle of the value, in fact, and we use this later on. So having found the characteristic for the heart rate measurement UUID, all that remains is for us to call the API function btget enable notify, and critically we specify the characteristic that we wish to receive notifications for in that call. Now, in terms of setting up notifications for heart rate measurements, we're done. So how do we actually receive heart rate data into our application so we can use it in our user interface? Well, if you recall, I earlier on defined a callback called notification CB, and here it is. When the Bluetooth sensor, the heart rate monitor strapped around someone's chest, delivers a Bluetooth notification containing the heart rate measurement characteristic, this method will get called, and the value parameter will contain the heart rate measurement value in beats per minute. So all we need to do is take that value and make use of it in some way. Now, just to be safe, we check the handle of the characteristic value that we're receiving to ensure that it is the value that we're interested in, because we made a note of the handle value earlier on in the process. And when that proves to be the case, we store the value away in a singleton that we've created, our heart rate data container, and we indicate to the user interface that it has a new heart rate measurement to display. And that's that. That's how we receive and utilize heart rate data from the Bluetooth device.
Thank you, Martin. What you've seen is an overview of the Bluetooth Low Energy architecture and an example of a real BlackBerry 10 application based on that theory. The code can be found on GitHub, and a more detailed article can also be found in the support forums. Martin and I are available on Twitter and are happy to help and answer any of your questions. Thank you for taking the time to view this video. We hope you enjoyed it, and we hope you found it useful.